Hello and welcome again to UCLA Extension University. This is high-rise plumbing design and this is week 7. We're looking at more hot water systems and we're also going to look at hot water recirculation systems. So once we've determined our loads and how we're getting the BTUs to meet our loads, we can start evaluating methods for collecting that energy and transferring that energy into the domestic hot water, which is what water heaters are all about. Transferring energy from one place to another. It's important to note that balancing is absolutely the number one biggest problem with high-rise hot water return systems. Always specify that all balancing shall be performed by an independent third-party test and balancing contractor. Then make sure that you receive all the balancing reports. Make sure they're valid, they're for the building you're looking at, they weren't all copied from one another, and that they didn't just make the stuff up. And we need to do this before we sign off on anything, and that includes the punch list, and that includes commissioning. Make sure that we specify low flow circuit setters and they're more sensitive and they work better, and that the contractor actually installs them as specified. No matter how good our design though, if it is not installed properly and maintained and properly balanced, we can't expect it to work as intended. And we have to watch that the contractor actually installed these things, because I've seen, I saw a hotel project, high-rise hotel, 65 risers, and all they did was put in ball valves. They kept saying they had the circuit setters in. I kept asking to see them, and then the system was having issues, and it's because they had these ball valves in. We had to get a third-party contractor to come in to install the circuit setters because of some contract disputes, and then we got the system balanced, and lo and behold, it worked. Okay, so that's a major problem, and you have to watch out for it. So since the T&P valves are limited to 150 psi, we can only cover about 2 vertical zones within one system. But you know what? That's only for upfeeding. And what does that mean? Well, for one thing, it means that we're limited to serving only about 250 feet or so. And that's about 23 floors. We could do some quick calcs and do a rough estimate to see that 150 psi and minus about 30 psi at the fixture. Of course, that varies. Some showers are 40 psi or more. And that leaves us with 120 psi. Maybe 20 psi will be lost through the valves, thermostatic mixing valves, and friction. And that leaves us with about 100 psi to overcome the static pressure. 100 psi, if we convert that to feet, that's 231 feet of static that we can overcome with that 100 psi, or our total of 150 psi. So we have a floor-to-floor height, let's just say, is 11'6". 231 feet divided by 11.5 is about 20 floors. So roughly 20 floors could be covered with that 150 psi. So what do we do about that? Can we get beyond that barrier? Well, sure we can. We have some options for supplying separate zones for every 2 pressure zones. But we can also incorporate downfeed systems, and other things. And we have a few slides here that you may recall from last week, session 6B. So let's take a look at them again and go into a little more detail. It's important to remember that these sketches are diagrammatic. Much like most of the work that we do, it's diagrammatic. We always have notes. Do not take the dimensions off of these plans, blah, blah, blah. We need to connect below the top floor so that the air can escape from the upper floor. We will always include automatic air relief valves, but we run the horizontal connectors below the top floor whenever possible and practical, just for that added security of knowing that when those fixtures are used at the top, the air comes out. Can solve problems in the future. So let's look at these sketches. Again, they're pretty simple. They're hand sketches, but I think they can demonstrate the principles fairly easily, and maybe not having all that other detail helps to make them more clear. So here we see a system with 3 zones. Each zone has its own water heater. They're all down-fed. They all have their own recirc system. So we provided a separate water heater for each of the zones. Now we could take the same system with the 3 zones and we could repeat this arrangement multiple times for taller buildings. Could we go beyond 3 zones? Yes, we could. And remember, because we're not upfeeding, so we have some extra latitude there. But then, however many zones we have, we can multiply that going up the building to build a system for whatever height we need. Now this applies to cold water also. And remember to run the cold water and hot water zones together. We can have downfeed and upfeed in the same systems, but for every zone, if the cold water downfeeds, the hot water downfeeds, and vice versa. Don't mix them. Don't have cold water upfeeding and hot water downfeeding. Theoretically, the pressures balance, but in real life scenarios, doesn't work exactly like that, and you can have balancing problems. There are more things that can go wrong to cause some anomalies and have your pressure balancing off. Could play havoc with your mixing valves. So with this approach, we sized the domestic booster pumps to provide just the right amount of pressure at the top. And we do not need to have PRVs at the top zone because we designed the system for just the right amount of pressure at the top. This is not just for sketch 1, but this is always, but that is why we don't need the PRV at the top. The mid zone needs a PRV because we're picking up pressure from the static as it goes down, and the low zone also needs a PRV but with different settings. We add PSI from static as we go down the downfeed system. We lose this PSI on the return side going back up to the heaters, so it kind of cancels out. So you don't have to account for that pressure to get back up because you picked it up when you came down, and then as you go up, it goes down. The pressure is reduced till it gets to the top. But we have another consideration: friction. And friction through the piping and the valves takes away some of the pressure. So it was always going to be a little bit less coming back on the hot water return side than it was on the hot water supply side. This means the pressure for each one of those 3 zones will be slightly different because they all had different size loops. less piping and more piping, so they're going to have more or less pressure loss. So if we connect them together, we need a way to balance the pressure, and this could be tricky. Generally, the key to sizing hot water return loops is that we size the heat loss based on the entire system. All of the hot water in hot water recirculating piping is like a radiant system. It's giving off, it's losing heat. Even if it's insulated, it's losing some heat. If it's not insulated, it's losing a lot of heat. But we size for the pressure drop based on friction, of course, but only for the longest leg of the system. If we can pump through that leg, then we can get through any other leg or circuit. Remember that the water doesn't go through all of the circuits, it goes through its own circuit. Each zone also needs a hot water recirculating pump to overcome the PSI loss through the piping and the valves. But because each zone has its own water heater, there is no problem balancing the zones back to the water heater, theoretically. Let's look at sketch number 2. What's different? Well, it's downfeed again, but we went up to one single water heater. So it's similar to one, but it's different. And we have only one water heater serving all the zones. This scenario could also be repeated multiple times for taller buildings. Think of it as a cookie cutter. With this approach, we need to balance the three systems as they connect at the top. We do this by providing PRVs with remote sensing piloted valves. These remote sensing piloted valves sense the pressure of the loops and modulate the pressure to allow them to blend. They sense the PSI of the loops and modulate them and allow them to blend, as we said. If we did not balance the PSIs, the higher pressure would overpower the lower pressure circuits and cause short circuiting. You can't push the low pressure side into the high pressure side. The high pressure will overrun it and you will not be able to get that water to circulate properly. What happens then? It causes some of the loops to stay hot while others become cold. You can also put all the flow through less loops than what the pumps were designed for, what they were sized for, and what happens then, we cause an increase in velocity and we have premature pipe failure because the water is circulating very quickly through one loop and not getting to the other loops. So we exceeded our 3 feet per second is the limitation that I use for hot water recirculating because it's always moving, it's hot, it has air entrained in it, it's erosive. Problem is, these valves require maintenance. All PRVs require maintenance and are generally not maintained properly. Again, make sure the contractor actually put in the remote sensor because that can be an option on the valves and they might try to, let's just say they forgot to put it in. I'm not saying they would do it on purpose. PRV failure is very common. It's one of the main causes of problems with all pumping systems, not just hot water recirculating, but for domestic pumping systems also. Here's sketch 3. Again, we have one water heater and it's feeding all the zones, and we have a PRV for zone 2, PRV for zone 3, and then we have PRVs on the backside, the remote sensing piloted valves to balance because you're going to have different pressures as they connect back together. And then you have one recirc pump at the bottom feeding up, and you have a PRV at the top again. So let's take a look at that again. It's similar to Sketch 2. We still have only one water heater serving all the zones, but we're connecting returns together and running only one return back up to the top. So that saves some piping. But the pump gets bigger. The pump gets bigger, and that causes problems because we do this again by providing remote sensing PRVs on each loop, provide another remote sensing piloted valve on the cold water connection, but we still can have balancing problems. But the main problem with that is that one pump that you have at the bottom of those zones is big, and it's usually going to be a base mounted pump, 3,500 RPMs. It's going to be noisy and a lot of vibrations, and that's not conducive to a domestic residential environment. Businesses don't want to hear the noise either. What I like to call a new approach to hot water return, and it's been around for a few years, but it's what we do now to eliminate most of the problems with balancing and some other problems. Like I said, it's been around for a few years. It's been documented in magazine articles. I'm sure you've seen something somewhere in PS&D or our new Plumbing Engineer magazine. Here's what it looks like. It's also called the zone system. So for each one of the zones, it has its own heat exchanger, a plate and frame heat exchanger, and it's getting the heat for that to maintain the hot water temperature in the loop by picking up some heat from the hot water supply loop. Okay, so it's stealing a little bit of hot water, but not that much. A little bit of energy is coming off there, but it's still a very efficient system. So this is installed on each zone. Again, it picks up some of the heat from the hot water supply to maintain the temperature in the loop. We still need pumps and PRVs, but they're very small. And the balancing is so much easier and more reliable because you're only balancing that zone. It's very easy to get back into the main. It also makes the hot water return pipes or pumps smaller and quieter, and that's really important. The main RCP pump for some of the other conventional systems that we talked about are large base mounted pumps. High RPMs cause a lot of noise. So this zone system was developed by Mark Collis of Bornquist. I don't know if you know him. Might have met him at ASPE convention or somewhere else. His contact info is available upon request. Just let me know and I'll get it to you. Let's have an example. Following is an example of a high-rise project. We'll include some pressure calculations, some diagrams and schedules, and we'll throw in some details. This should help us to get a better grip on the principles that we're discussing here. This is a spreadsheet that I made. I call it a zone map. It gives me the opportunity to put in the heights, and I can have it calculate the floor-to-floor heights and the static pressures, and then I can look at each zone. I can see if I'm upfeeding or downfeeding, what kind of pressure I'm getting, and also what my PRVs are seeing, what pressure is in, what pressure is out. So you might notice that we don't need a PRV on the top zone, but on the mid zone and low zone, we're down feeding in this case. So you see that the pressure coming in is 81.76 for the mid zone and 135.99 for the low zone, because we're pumping up with the cold water main, and then we're coming down to a downfeed system on the cold water distribution and on the hot water. So you see the PRV outlet is only 35 psi, and then it's picking up, because it's downfeeding, it's picking up pressure down to the bottom. We can only put 80 psi to a fixture, so this doesn't account for friction. So if we have 81 psi at the bottom of the zone, that's just fine. It's not really going to be 35 to 81 psi at the fixture. It'll drop off a little bit. So here we have, in the riser diagrams, it's cut in half because it didn't fit on the sheet. And on this PDF, you can't really see the details, but maybe you get the general idea. Notice that the lower levels are blank because that was parking. And at the time this schematic design was going on at this level, we didn't have all the details. So we're just trying to show the basic concepts of how we're getting the water in and where's it going. Looking at how we're going to break it down. Here's the top part of the riser. Again, you can't really read all the details, but you can see that it feeds up to the water heaters, which are at the top, and then they downfeed to the zones. And then we have hot water recirc coming back at the bottom of the zones. Here's a detail. And at this point of the project, in this case, we had gas-fired water heaters, and here you can see the tanks and the water heaters and an expansion tank. And this, I believe, is very similar to what you see on the Lochinvar website. But all of the manufacturers have similar details. So please look at that and use that as a resource. Here's the water heater schedule that goes with that diagram. We have 2 water heaters at 96% efficient, 1 million BTUs each, and the rest of the nomenclature's there. We have a few notes included also. Here's the storage tank schedule. We had 2 650-gallon storage tanks, and this has a few of the bits of the nomenclature for those. Then we also included on the drawings things like the main valves, circuit setters, the mixing valves. We use the Holbys. Holbys are very good for mixing at the actual water heater, not at the fixture, but at the heater. You need a PRV schedule. These are the hot water PRV stations. It's not in a schedule format, but it's easier to see here in this format, I believe. Here's the hot station zone 4. And then we look at the zone equipment. By that we mean those zone recirc systems, secondary heat loops. So they're all going to need a heat exchanger. It's a plate and frame heat exchanger. And those are sized based on the load. In this case, we have 40 plates. You might have more plates depending on your loads or less. I would consult with the manufacturer when you're following these approaches to make sure that you have everything set up properly. These are from Bell & Gossett, and they are the originators of the system, but anybody else, your other manufacturers, should be able to help you also. Then we have the zone valves. For each zone, they have their own search setter. And then there's a tank, pressure tank, zone relief valve, zone valves, etc. Another option as opposed to gas-fired water heaters, on this project we're simultaneously designing for gas-fired heaters and also for uh, hot water to hot water heat exchangers based on taking water from the boilers. During design development and schematic stages, it's often the case that you don't know what you're going to have, and you have to design more than one system simultaneously as the details shake out from the project development. So later, this option was removed from the project, but we still had gone through the selection process during the schematic design. So this is a common practice in our modern era. Everything's a rush. In this case, we had 3 boilers, and they were 1 million BTUs each. They were modulating condensing boilers. I know that you notice that this is 50% more BTUs than we had on the other because we have 3 units here. We only had 2 on the other system. Don't forget the building's changing in various ways as we're developing the project. We have and that would require boiler side pumps. And again, I wouldn't size all this stuff myself. I would work out the major parts and consult with the manufacturer. The triple duty valve is really important too, and it needs to be sized properly and selected properly. You need the right kind of valve for your application. Air separators are required for boilers. I'm including the domestic water pump also and the cold water PRV info just for your information. It might help to understand the system a little better. We're not going to go through all of this now, but I'm including it here. But you can see that we have stainless steel submersible turbine pumps. We have 3 of them. They're VFDs. I always use VFDs. Some of the controls and accessories. All this stuff needs to be specified. See a NEMA 1 cabinet. We don't want it to get wet. A few other details, warranty information. Then our PRVs. You know, if you're feeding them both the same way, the cold water and hot water should have the same pressures. Sizes can be different depending on your loads, but the pressures should be the same because the zones are the same. And we want them to be balanced. So here's an example of the floor plan in the basement. This was modified several times because there's a lack of space. In this version here, I think that the electrical spaces are undersized. And the basement is smaller than the building footprint because of the surrounding structures. It's surrounded by other high rises, and it was very expensive to provide the shoring required at the property line. So they brought that in and saved hundreds of thousands of dollars just on that part of the project. But it made it tight for all the equipment. So it's a little blurry, but in the lower left-hand corner of the building, that's where the domestic water comes in on the side, 2 12-inch. This is not the underground, so you don't see the underground piping. But in that first bay there, you see a rectangle. That's where the pumps are, the domestic water pumps. Very small, stainless steel, very nice system. This was from AMT. I can get you their contact info also. And you see the red pumps over to the side are the fire pumps. They're here, we started off with the biggest because we were trying to get space. And that's common, especially in high-rise buildings. You got to try to get the space because they're never going to want to give it to you anyway. And these are um, split case horizontal pumps, so they take up more room. And you can see we're taking up that whole lower right hand corner. You need to have 3 foot clearance in front of the controls, the control panels. So then we devised another scenario with going with vertical turbines, and they cost more, but it's easier to install and they take up less space. And we're not really talking about fire protection in this class, so we'll just leave it at that. So if you remember, we talked about when does a building height start to make a difference in your considerations. We have some typical limitations of components and materials, such as the piping, which is commonly 500 to 600 psi. The valves, it gets more expensive with the high pressure valves, but now you can even get 600 psi valves at Home Depot. That doesn't mean that they're the best quality. I'm not saying they're not good quality. I'm nothing against Home Depot. I'm just saying that you have to be careful with that stuff too. The pumps, high pressure, large horsepower, constant speed pumps exhibited issues with control. Now we have variable speed pumping, which makes this much easier. I use variable speed for everything. Water heaters. The TMP relief valves are limited to 150 psi, so that can restrict you to 2 pressure zones depending on how you're feeding the system. Hot water recirculation is problematic whenever you have multiple zones, but we dealt with a lot of that in the previous materials. Some other things to consider: as we get to about 2,000 feet above sea level, we start to encounter effects on the air-fuel ratio in gas-fired appliances. That's because we have a lower oxygen content as the air gets thinner. High altitude means less oxygen, and that means that we need less fuel. And less fuel means a smaller orifice on the boiler or the gas-fired appliance. This effect can be very dramatic at higher elevations, and if a water heater is modified for high altitude, we need to make sure that it's derated or the fuel must be devalued. If you do one but not the other, or not both, you can do one or the other but not both. For more information on this, there's a link right here for a short paper on the effects of altitude. Now remember, some of our buildings now are 2,000 feet high or 3,000 feet high. Who knows what the limit will be? In the era of the Sears Tower and Empire State, etc., those are around 100 stories, maybe 1,600 feet, but now we're going higher. Plus, um, you're not at sea level, so it's having an effect. But if you have a Burj Khalifa or one of those super tall buildings, your gas your gas considerations are different at the top of the building than they are at the bottom of the building. Also, the temperature is different and other conditions. One last thing I'd like to mention as far as height goes: stack effect is also dramatically affected by high flues and elevations. We can take care of a lot of this with powered exhaust systems from people like Exhausto or Journalin, but we won't go into that any further right here. Remember that the flues always have to be coordinated with the HVAC because they're providing the air. You get the combustion air in the exhaust from HVAC, and all these things must be worked out together. That's one of the most common problems that we have with water heaters is combustion air and the flue. If you specify a water heater and then the contractor installs a different water heater Even if it's the same BTUs, it might not have the same air and exhaust requirements. All this has to be coordinated carefully, and if it's changed, we need to make sure that it works. You're going to need to work with the HVAC engineer and also the manufacturer, because a lot of it is based on manufacturer's recommendations. If the duct is drawn a certain way on the plans and that meets the requirements, and then the contractor offsets it to go around something, he might have just ruined the whole effect, and it might not function properly. So all that has to be signed off. You need to get the shop drawings, make sure that you look at the shop drawings and the HVAC engineer looks at the shop drawings. So we have different types of water heaters. There's storage types, instantaneous, which I call on-demand type. Nothing is instantaneous. Then you have semi-instantaneous, and we heat exchangers of different kinds, gas-fired heaters, steam-fired, electric, all types. And here's a look at how they look these days. Well, maybe not. This is old, but you know, the basic function has remained the same, even though they've changed in technology and performance over the years. But they're still doing the same thing, heating your water. Here's some more modern versions and some different manufacturers. It's just a random group of manufacturers, no particular reason to have them here. Some of my favorites aren't even up here. This goes back to the basics. Sometimes you have to consider this kind of information when you're choosing what type of system you're going with. That's not always a luxury that you have. You might be forced into one or the other. Sometimes you might have to provide information such as this to help the owner or the project manager or construction manager choose what they're doing, or you might have to show them why the change they made has such an effect on the system. This is an example, random location. It's not going to be the same for everyone. It shows the water heater annual operating costs for a family of 4 in some undisclosed location. According to this, the electric water heater would cost a lot more to operate than oil-fired or gas-fired or heat pumps. The oil-fired is very popular in the northeastern United States. They don't have the gas infrastructure that we have in other parts of the country, so they can't really rely on natural gas. So you see a lot of fuel oil-fired units there. It has some advantages. You can contain your oil right there, so you don't have to worry about a main breaking and you don't have gas. But anyway, you have to consider that each one of those for your particular location. Again, this is going to vary. A lot of places it's going to cost more for electricity, not all places necessarily. Gas has actually become a lot cheaper in recent years, and I think that green bar should be lower. Just something for thought. It always varies based on the location of the project. Thank you very much for listening, and we'll see you next time.